Alright, so let's get started. So last time we continued to look at the Lagrangian, and in particular we looked at the case when there were constraints and how to use the equations of constraints to, instead of reducing the number of degrees of freedom, to keep the bigger number of degrees of freedom and try to understand something about the forces in the system that are associated with those constraints. So we found that we used the results that we had from variational calculus, and if we have a Lagrangian L, and K constraints, given by equations of the form F1 of the generalized coordinates equals 0 all the way to Fk. So we call these holonomic constraints. Holonomic means that the constraints are between the generalized coordinates themselves, and that means that you can, in principle, use these constraint equations to eliminate some of the coordinates. But if you don't want to, you can use the method of Lagrange multipliers in which you would write a new Lagrangian, which we called L bar, and you introduce these lambda parameters, which we call Lagrangian multipliers. We put a minus sign in this case because the lambdas are arbitrary, right? So we can, if you remember from variational calculus, when we're doing this, we're adding a bunch of zeros. So whether we add zeros or subtract zeros doesn't matter. But if we put a minus sign, these terms are like additional potential energies that you're adding to the Lagrangian if you define a new potential energy by lambda I Fi. So these are like potential energies. And by like, I mean in the mathematical sense. And for like potential energies, in the most general case, we can treat them as generalized potentials, and then they would have some sort of generalized force that's associated with them. So there's a generalized force for each I of the K potentials that you add, and that generalized force is associated, there's one generalized force for each J degree of freedom. And simply putting this into the definition of a generalized force from a generalized potential, that generalized force is d by dt of di Fi by di Qj dot minus di Fi by di Qj. And of course, the reason the force has that particular mathematical form is that that's the Euler-Lagrange equation, or at least it looks like the Euler-Lagrange equation and then it adds nicely into the t minus v. Okay? And so what we found was that constraints are related or maybe related is the wrong word. Let's say constraint equations can be used to learn about the forces associated with those constraints. And then we finished last time by doing an example of a hoop rolling without slipping down an inclined plane. Even though there's only 1 degree of freedom, we decided to use 2 degrees of freedom and then add an additional constraint for the rolling without slipping. And so we described the position of the hoop by both the rotation angle as well as the distance down the plane. And then we added this additional constraint, and we found that there was a force associated with that constraint, a generalized force that looked very much like a torque that makes the hoop turn. And so it sort of makes sense that this idea of rolling without slipping is associated with some sort of force that makes the hoop turn. Okay. Any questions about what we did last time? Good, because we'll do it again right now then. So let's do example 4.5 in the notes. And it's the same problem. We have an inclined plane. Makes an angle theta. And we have a hoop. Of mass m. And radius r. We'll put in a coordinate system. And let's introduce a vector or a one-dimensional coordinate r. So r is not a vector, it's the distance from the origin to the point of contact of the hoop. So in the previous example, we described the position of the hoop by little r and phi, and that we added a constraint to bring the number of degrees of freedom, or that's equivalent from bringing the number of degrees of freedom from 2 to 1, and that constraint was the rolling without slipping. But in principle, there's 3 degrees of freedom, right? The hoop can be anywhere in the xy plane, and then it could be rotated by any angle phi. The constraint that the hoop is on this inclined plane means that x and y are not independent, right? So let's now do the problem with 3 degrees of freedom. So in principle, the number of degrees of freedom is 1, but we choose 3, and we'll use phi, x, and y plus 2 constraints. So the first constraint is a constraint of being on the inclined plane. And so let me use x and y as the position of the point of contact of the hoop. So the constraint of being on the plane is that y actually depends on x, right? So we have y over x equals tan theta, since tan theta is constant. And so we can write that, let's call that F1. We want to write the constraint as something equals to 0. So we can write that as y minus x tan theta equal to 0. And the second is the rolling without slipping. So remember, in the previous problem, we could write that as r, little r equals big R times phi. All right. And recall that, for example, y is equal to little r sine theta. So that means that y over sine theta, which is also equal to x over cos theta, and that's equal to big R times phi. And so we can write this as F2. And we can write that as y over sine theta minus big R times phi, which is also equal to x. We can use whichever one we want. X over cos theta minus R times phi, and that's equal to 0. Right, we can use either equation because basically we can put F1 into F2. But we'll just choose one, and it doesn't matter which one we choose. Okay, so that's our constraints. So let's look at our Lagrangian. So the Lagrangian is T minus V. All right. So T, the hoop has two types of kinetic energy, a rotational and a translational. So rotational energy is half big M, big R squared, phi dot squared, plus half M for the kinetic energy, x dot squared, plus y dot squared. All right, last time we had that as r dot squared, but now we're using 2 degrees of freedom. And then we have a potential energy, which I'm going to write as mgy. So technically that's not quite correct, right? The potential energy is mg, and instead of y, it should be the height of the center of mass. Last time we included a constant k that we carried around which was the constant offset between the point of contact of the hoop and the center mass. And then we found that when we took the Euler-Lagrange equations, because we take the derivative with respect to phi, x, and y, any constant term just drops out. So it doesn't really matter what we use as the constant offset for the potential energy. So I'm just not going to include it this time. And so we can build our modified Lagrangian, L bar, to be L minus lambda 1 F1 minus lambda 2 F2. So that gives us L bar is equal to a half M big R squared, phi dot squared. I guess there's no little r, so I don't have to say big R every time. Plus a half M x dot squared plus y dot squared minus mgy, and then minus our first constraint minus lambda 1. And our first constraint was y minus x tan theta. That was F1. And then minus lambda 2, and we'll choose, let's say, the y version. So we have y over sine theta minus r phi. Okay. So now we use, well, I guess we go to the next page, and we apply the Euler-Lagrange equations to get the Lagrange equations of motion. Alright, so now by now we know these by heart. d by dt of di-L by di-Qj dot minus di-L by di-Qj, I guess it's L bar in this case, equal to 0, where Qj will be equal to phi, x, and y. So let's do x. So if I look at the Lagrangian, the only term with an x dot in it is the kinetic energy, a half m x dot squared plus y dot squared. So di by di x dot of that is mx dot, and d by dt of that is mx double dot. Then I look for terms that depend on x, and we have only the term with the first constraint, the lambda 1 times y minus x tan theta. And so if I take, so that term, there's two minuses in it, right? So then it's plus in the Lagrangian, and the modified Lagrangian, it's a plus lambda 1 x tan theta. So if I take the derivative with respect to x, I have x1, or lambda 1 tan theta, and then minus because of the minus sign in the Lagrange equation. So that gives me mx double dot minus lambda 1 tan theta equals to 0. Alright? So let's do the same thing for y. So again, I'm going to have the my double dot term. And now if I look at the terms that depend on y, I have the gravitational potential energy term. And so that's going to become a plus mg. Then I have the lambda 1 y term. So if I take the derivative with respect to y, that's just lambda 1. And then I have the last term, minus lambda 2 y over sine theta. If I take the derivative with respect to y, I get plus y2, or lambda 2, sorry, over sine theta. And that's got to be equal to 0. And finally, we can do phi. So phi dot, the first term has a phi dot in it, so that gives me mr squared phi double dot. And then the only other phi term is in the last one, the lambda 2 times minus lambda 2 times minus r phi. If I take the derivative with respect to phi, I get lambda 2 times r. And with it's an overall plus sign in the Lagrangian, so it'll be a minus sign in the Euler-Lagrange equation. And that's minus lambda 2 r equal to 0. So again, here now we have 3 equations and 5 unknowns. The unknowns are x double dot, y double dot, phi double dot, lambda 1, and lambda 2. So this is sort of generally true that this is the technique. To get the additional 2 equations, we take the second derivative with respect to time of f1 and f2. And so f1, remember, is that x equals y over tan theta, and tan theta is a constant. So if we differentiate that twice, we just immediately get that x double dot is 1 over tan theta y double dot. And similarly, so that's f1. Similarly, from f2, we can get that phi double dot is equal to 1 over r sine theta y double dot, because since the r and theta are constants, the time derivatives are trivial. And so now that gives us our additional 2 equations, so that we have 5 equations, 5 unknowns. I don't know if this will be useful, but let's label the equations. 1, 2, 3, 4, and 5. Maybe it's less obscure when I solve them. So let's take equation 1. So equation 1 gives us that mx double dot is equal to lambda 1 tan theta. And then if I use equation 4, where x double dot is equal to 1 over tan theta y double dot, I can write this as lambda 1, is m over tan squared theta y double dot. There's many ways to solve this. I'm just choosing one way to solve it. Okay. I can take equation 3. Equation 3 tells me that mr squared phi double dot is equal to lambda 2r. And if I put f2 into there, I can get lambda 2 in terms of y dot, and that gives me lambda 2 is m over sine theta y double dot. So here I've used equation 4, and here I've used equation 5. So let me now put all of this into equation 2, which I guess will happen on the next page. So equation 2 is my double dot plus mg plus lambda 1 plus lambda 2 sine theta, my double dot plus mg plus lambda 1 plus lambda 2 over sine theta equals to 0. So I can write that as my double dot plus mg. If I replace the lambda 1 now, that's m over 10 squared theta y double dot, and the lambda 2 over sine theta term, that's going to be m over sine squared theta y double dot equal to 0. So let me factor together all the terms. Well, first of all, the m's cancel, right? Every single term has an m, and then it's equal to 0, so I can just drop the m's. And then let me factor the y double dots. So I have the first term is a 1, the second term doesn't have any, the third term is a 1 over 10 squared theta, and the last term is a 1 over sine squared theta, and then plus g equal to 0. All right. So we can simplify this trig expression here. Let me write this as 1 plus, so tan is sine over cos, right? So 1 over tan squared is cos squared over sine squared. The last term is 1 over sine squared theta. Right? So if I multiply this, well, I guess I don't have to tell you how to add fractions, right? So I put everything on the same denominator of sine squared theta. That just means I have to add multiply the 1 by sine squared theta. So that means I have sine squared theta plus cos squared theta plus 1 all over sine squared theta. Alright. And so of course the sine squared theta plus cos squared theta is equal to 1. So I have 1 plus 1 over sine squared theta. So I get y double dot, times 2 over sine squared theta plus g equals to 0. And so I can solve for y double dot, and I get that y double dot is minus a half g sine squared theta. I've already expressed all my other variables in terms of y double dot, right? So that immediately gives me lambda 1. So lambda 1 was equal to m over tan squared theta y double dot. And so that's equal to minus half mg cos squared theta. Because 1 over tan squared is cos squared over sine squared, and the y double dot has the sine squared. So the sine squared in the denominator cancels. Similarly, lambda 2 is given by m over sine theta y double dot. And so lambda 2 gives me minus half mg sine theta. You may notice that lambda 2 is in fact the same as the lambda that we got in the previous example where we only used the one constraint of rolling without slipping. So lambda 2 has something to do with the force that makes the hoop turn. We can also write, if we want, x double dot is equal to minus a half g cos theta and y double dot, phi double dot, sorry, is equal to minus 1 over 2r g sine theta. And that's just simply given by substituting the y double dot into the two additional equations that we had from the constraints. Okay, so the problem is solved. Let's examine, however, the generalized forces that we get from this. Let's go to the next page. So again, we use our formula for a generalized force that Qij is lambda I times d by dt of di fi by di qj dot minus di fi by di qj. Now none of our constraint equations actually dependent on velocity, right? So that first term is 0. So we know that in this case here, it's just going to be minus lambda I di fi by di qj. And recall, our constraint equations were given by F1 is equal to y minus x tan theta, and F2 was given by 1 over sine theta times y minus r phi. That's the same as 1 over cos theta x minus r phi. Okay. And the lambdas we also need, and we just solve for them. So if I plug all this in, I'm going to get Q1x is equal to lambda 1, which is minus a half mg cos squared theta times di f1 by di x, which is minus tan theta. small type on the notes. I forgot the minus sign. So if I just write tan theta as sine over cos, that gives me half mg cos squared sine theta. Is that right? That can't be right. No, that should be, it's a mistake in the notes. That should be just cos, not cos squared. Q1y, so that's minus a half mg cos squared theta, right? That's the lambda 1. And then times di f1 by di y. Well, that derivative is just equal to 1. Q1 phi if I look at the di f1 by di phi, that's equal to 0, right? So that's equal to 0. Because di f1 by di phi equals 0. And then let's do the Q2x. So lambda 2 is minus a half mg sine theta. And the derivative of f2 with respect to x is 1 over cos theta. And it's minus that, so it's minus 1 over cos theta. And that just gives us a half mg tan theta. And then finally, Q2y is equal to minus a half mg sine theta. That's lambda 2. And the derivative with respect to y of f2 is 1 over sine theta. So that's times minus 1 over sine theta. And that just gives us a half mg sine theta. A half mg, sorry. The sine theta canceled. And then finally we have Q2 phi. So that's minus a half mg sine theta. And then the derivative of f2 with respect to phi is minus r. And so that's times r. And so that gives us minus a half mg sine theta r. And so these forces, so the generalized force in x, for example, would be Q1x plus Q2x, and the generalized force in y is Q1y plus Q2y. And in phi, it's Q1 phi plus Q2 phi. So they're not super obvious what all these forces are, but they're associated with the normal force between the hoop and the plane, and that Q2 phi is the same one that we found earlier, and it's associated with the force of constraint that we had that makes the hoop turn without slipping. And so that's sort of like the torque on the hoop that's required to turn the hoop at the right speed so that it rolls without slipping, or the right acceleration, sorry. Any questions about that? So it should be clear now that we're working towards a way of doing classical mechanics where we don't need forces so much, right? We never drew a free body diagram for this relatively complicated problem of a hoop rolling down a hill, and we were able to write it down pretty quickly, the solution. We made it much more complicated here by adding these extra degrees of freedom, but you know that we didn't have to do that. We could have done it with 1 degree of freedom and gotten the equation of motion essentially in a one-liner, compared to what you would have had to do with the vectorial method, where you had to draw all the forces at the point of contact. So the concept of forces, you see, we sort of reintroduced it by adding in the constraints to the system, but if you have the option of doing this without worrying about the constraint equations and using independent coordinates, then it's unlikely that you'll end up with needing the concept of a force. Of course, we know that's not true when the forces are non-conservative. Remember, we have, in principle, on the right-hand side of the Euler-Lagrange equation, we have it equal to Qj of the non-conservative forces. However, most forces are conservative. And in sort of Newtonian mechanics, when you have a non-conservative force, it's because usually you're not considering the system as big enough of a whole, right? So if you have a block sliding on an incline, you could have a friction force, and that's not a conservative force. However, if you consider the block and the incline as a system of the two components, then the friction is actually an internal force to that system. We know that those internal forces don't usually come into play. And if you really do a detailed description, for example, of these friction forces, those forces usually come from electromagnetics, right? It's the interaction of the atoms in the two materials, more precisely the interaction of their electrons, that give rise to this friction force. And so if you really modeled that very accurately, then you would actually be using electromagnetics to model friction, and electromagnetic force can be written as a conservative force. In fact, we wrote that out as an example when we use a generalized potential. So if you do a detailed enough problem and you include everything, ultimately you only include conservative forces, because there's only 4 kinds of forces, right? The strong and weak nuclear forces, gravity, and electromagnetism. So ultimately, you don't need to consider non-conservative forces. It's sort of only in the toy examples of undergraduate physics. But as we generalize to more complete description of physics, these non-conservative forces are not that important. So from now on, we'll usually restrict ourselves to systems where all the forces are conservative. Okay. So you may recall that everything that we've done so far was under the chapter heading, the Lagrangian from D'Alembert's principle. Okay. But there's another way to obtain all of this physics, and that's actually the much more general way, and it's called Hamilton's principle. This will actually require, This will not require us to do much math, since we've already carried out most of the math, either in this chapter or in the chapter on variational calculus. So Hamilton's principle, the idea is that a physical system should be fully described by some function that depends on the generalized coordinates, the generalized velocity, and time. So a system should be described by a function that depends on the generalized coordinates, generalized velocities, and time. And of course, we'll call that function L. So given that's true, then the equations of motion are given by requiring that the integral from between two different points in time, t1 and t2, of this function L dt is stationary. Right, and that's Hamilton's principle. Hamilton's principle says that the equations of motion are required, are given by requiring that some functional, and a functional is an integral of a function, is stationary. And so we've already done all the groundwork, so we know that from variational calculus, this means that this function L, whatever it is, must satisfy the Euler-Lagrange equation. So that's d by dt of di L by di qj dot minus di L by di qj. All right? And then we know from what we just done from D'Alembert's principle that L defined to be t minus v works. So I clearly don't need to redo all the math to show you that L equals t minus v works, since we did it the other way around. And we did it with D'Alembert's principle, which includes only t, and we took the conservative forces and we showed that it can be written as v, and so we could write D'Alembert's principle as something that looks like the Euler-Lagrange equation with this new quantity L. So Hamilton's principle is just saying it the other way around. There exists a quantity L whose functional must be stationary, and then that tells you that variational calculus means you can apply the Euler-Lagrange equation to L, and that's what gives you the differential equation of motion. Okay. So let's pretend that we don't know that L should be t minus v. Okay. Let's start a new page. So let's ask ourselves, what is L for a free particle? So we're just going to ask ourselves, mathematically, what could L possibly look like for a free particle? Okay? This is actually, I thought this was kind of a fun derivative in the Lifshitz textbook. So we want to find this L that gives the equations of motion through the Euler-Lagrange equations for a free particle. So a free particle really means a particle in complete empty space, right? So there are no forces, and there's no preferred direction, right? So let's pretend that we have two frames of reference, inertial frames of reference. So we have this one coordinate, x and y, and then we have some other coordinate system, x, y prime, and x prime, y prime. And maybe that coordinate system is moving with a velocity v. I don't know how you indicate that. Let's put a velocity, capital V vector, on the origin of the system. And let's say that we call the origins O primed and O. And let's say that the origins coincide at t equals 0. So our main requirement is that in two inertial frames of reference, whatever this L is, it shouldn't depend on what inertial frame of reference I'm in. They should both describe a free particle. Okay? So if we have this particle and we give it a position in the primed reference frame, that's going to be equal to the position in the unprimed reference frame plus this velocity vector times t. So I would say that's how position transforms. Okay? And similarly, the speed or the velocity of the particle in the primed system is the velocity of the particle in the unprimed system plus v. Well, a little bit ugly there. So we're talking about a free particle, right? So what else can we say? So for a free particle, this function L that describes from which we can ultimately get apply the Euler-Lagrange equation to and ultimately get the equations of motion, that L should not depend on where the particle is, right? Because remember, it's a free particle, so if it wasn't a free particle, maybe there's a gravitational potential energy, then clearly L does depend on position, right? But this is a free particle in empty space, so L should not depend on position. So that means that di-L by di-R, that's going to be equal to di-L by di-R primed. If we use some sort of generalized coordinate, that's going to be di-L by di-Qj. That's got to equal 0. So this L function that describes a free particle cannot possibly depend on position. Alright? So L can also should not depend on the direction of v. So little v, okay, is the velocity of the particle. So we have a free particle in space, and space is isotropic and completely empty. So this function that describes somehow how the particle evolves can't possibly depend on the direction of the velocity. We know that in an inertial frame of reference, there aren't special directions where your motion is different than other directions, right? So what that means is that if L can't depend on the vector v, L must depend only on the magnitude of v, at most. So the magnitude of v we can write as v squared. Well, it's the square root of v squared, right? So it's proportional to v squared. So that means L can only be a function of the velocity squared. So given that, right, so what we've said so far, the Euler-Lagrange equation, so we're working with Hamilton's principle, right? So Hamilton's principle tells us that there exists this function that depends on position and velocity, but for a free particle it can't depend on position. And for isotropic space, it can only depend on the magnitude of position, of velocity. And so given that that function exists, the equations of motion are given by the Euler-Lagrange equation, because that's what makes the integral, which we call the action, stationary. So this tells us that d by dt of di L by di qj dot is equal to 0. So qj is the coordinates that we're using to express the velocity, remember? This is the same as when we have a position vector for a particle, right, a vector r. We then express that in terms of our generalized coordinates, which are, there's an x component, so it's whatever generalized coordinates times x hat, plus whatever generalized coordinates times y hat, etc. So that's the same here, right? These qj dots are just the coordinates that we use to express v. So that's interesting because if d by dt, so the second term, of course, of the Euler-Lagrange equation drop, right? This is the di L by di q. So if d by dt of something is 0, that means that di L by di qj dot is equal to constant in time. So L depends on v, which can be expressed in the qj dots. And so if di L by di qj dot is equal to 0, or is constant in time, that means that the v can't change with time. So that makes sense, right? This is a free particle in completely empty space, and it has a velocity v. And we know from even Galilean mechanics that the velocity is not going to change. And this is the velocity, not the magnitude of the velocity, right? So just by these simple arguments we've already established, just mathematically from the allowable forms of L, that if there are no forces on it, then a particle's velocity doesn't change with time. All right, so that's F equals ma, but F equals 0. So that's actually a fairly powerful statement, right? And we haven't done anything like think about forces, or we just looked at the math of it from Hamilton's principle, and we've already uncovered part of Newton's second law. All right. So now let's ask ourselves, what could L actually look like? So L has got to depend on V squared, right? So it can only have terms in it. So let's say it's a polynomial. You can always write everything as a polynomial. So it could look like A times V squared plus B times V squared squared plus C times, V squared cubed, etc. So in principle, it can look like any polynomial, any functions of the V squared, right? Because we only know it must depend on V squared. But it also shouldn't be affected by a change of inertial reference frame. So this is L in the reference frame where V, the speed of the particle is given by V. So let's consider a new reference frame that's moving with a small velocity, which we'll call epsilon. So in that reference frame, V prime is equal to V plus epsilon. All right, that's what we had for our transformation equations, where initially we wrote as the epsilon as capital V, but now we'll write as epsilon. V prime has a vector on it. So let's consider now we have this Lagrangian that's potentially some sort of polynomial. So let's ask ourselves, what does L of V prime look like if we know, for example, L of V? All right, so that's L of V plus epsilon. Keep forgetting the vectors. So we know that that's got to be, can only be a function of the V prime squared, all right? And so that's got to be a function of L of V plus epsilon dotted with V plus epsilon. If I carry out the product, that's going to be a function of V squared plus 2V dot epsilon plus epsilon squared. All right, so remember, L is just some function of some variable, which I'm calling V squared. And then I want to know what that function is if I replace V by V prime. And so it's going to be that function of V squared plus 2V epsilon plus epsilon squared. So let's take epsilon to be very, very small, right? So if epsilon is small, then epsilon squared is really small. So let's do a Taylor series expansion of L of V squared plus 2V dot epsilon squared near with L centered at V squared. So remember, L is just some function And we're evaluating that function at v squared plus 2v dot epsilon plus epsilon squared. Right, where the 2v dot epsilon plus epsilon squared is a small number, so we can use the Taylor series, right? So this L of v prime squared is going to be roughly equal to L at v squared plus di L by di v squared times 2v epsilon dot epsilon, sorry, 2v dot epsilon, and then plus terms, plus terms that are of order epsilon squared. Alright? I'm basically saying epsilon squared is like 0, and so I'm evaluating L at v squared plus 2v dot epsilon, and then I do a Taylor series centered at v squared. Okay? So that's the form of L v prime, right? So now the Euler-Lagrange equation so that's very generally d by dt of di L primed by di qj dot minus di L by di qj equal to 0. And we already said that that's not going to, the second term is going to be equal to 0, right? So we have d by dt of di L primed, which depends on v squared, v prime squared, sorry, by di qj dot equal to 0. So I'm going to write that my L primed of v prime squared using the Taylor series that I had, right? So that gives me d by dt of di by di qj dot of L of v squared plus di L by di v squared of, or times 2v dot epsilon. So let's split this up into two terms. D by dt of di by di qj dot of L of v squared plus d by dt of di by di qj dot of di L by di v squared times 2v dot epsilon. And that's got to equal to 0. So the first term, that's equal to 0 from the Euler-Lagrange equation of L of v squared, right? Remember, I never said anything about what the function L of v squared looks like. But I know that in the inertial frame of reference, where the speed of the particle is given by v instead of v prime, it has to follow the Euler-Lagrange equation, so that first term has to be 0. So what we find is the second term, d by dt of di by di qj dot, di L by di v squared times 2v dot epsilon is equal to a constant, right? Also, this term here we already established in the first inertial frame of reference that V is a constant, right? That's why the first term is 0. And then the second, the second frame of reference, where the particle has a speed v prime, that frame of reference is moving at a constant speed from the first frame of reference. That's something we imposed for it to be an inertial frame of reference. So there's v dot e. That's the scalar product of two constant vectors. So that's a constant as well, right? So d by dt of the stuff after it is equal to 0. That means that di by di qj dot of di L by di v squared is equal to some constant. It's not equal to the same constant as 2v dot epsilon. It's equal to some other constant where I've absorbed the 2v dot epsilon in it. Let's just call that k. So for this thing to be true, that means L can't have terms in it that are higher in powers of v squared than 1, right? This means that L must equal, so it's precise, L of v squared must be equal to some constant times v squared. So this plus, b v squared, etc., that term has to be 0, right? Because you have this di L by di v squared, and then di by di qj dot of that equal to 0. So if di L by di v squared is still dependent on v, then di by di qj dot would not be a constant. It would also depend on v. All right. So what we find is that L for a free particle is equal to, the only mathematical form that could work is a times v squared, where a is some constant. So let's call the constant call it half m. So then the Lagrangian for a free particle is a half mv squared, where a half m is just some constant, right? And so if there are multiple particles in play, each particle is going to have a different a, or a different half m, right? And the behavior of the system is going to be described by the ratio of the values of those a's, or those half m's. So if you multiply all of the a's by some number, you're still going to get the same equations of motion, right? Because when you do the Euler-Lagrange equation, if you multiply L by some constant, then that constant will cancel out when you take the Euler-Lagrange equation, because it just comes out of all the derivatives. So what really matters is the ratio of this constant A for the different particles in the system. Okay? And that's okay. Obviously now you've understood that this is kinetic energy. Right? So we can call this constant mass. But we see that only ratios of mass change the behavior of a system. And that's because the equations of motion are not affected when L is multiplied by a constant. So this is kind of beautiful, right, that we've only just done sort of some mathematics and some requirements about space being isotropic, and we've derived kinetic energy from very, very basic principles and Hamilton's principle. And so the thing that Einstein realized, and that's the basis for all of general relativity, is that this constant here that we put into L, which we call the half m, turns out to be the same constant that dictates how strong the force of gravity is. And that's called the equivalence principle. I know we've mentioned this before. But here we saw how we just put in this half m in there because it looks like our familiar kinetic energy. And it's almost baffling that that is the same constant that comes in to gravity, because there's really no reason, right? We just saw here it's just a mathematical thing. I think that's a nice stopping point.
The Lagrangian equals potential energy. Where did you go, or can we derive? Because isn't the Lagrangian potential minus kinetic? I got them mixed up. This is kinetic energy, and it's kinetic energy minus potential. So can we derive the potential part as well? I can't hear you. Can you hear me? Yeah. We have the Lagrangian, which shows kinetic energy, but the Lagrangian is actually kinetic energy minus potential energy. Is there a way that we can get the potential energy term as well?
So from just purely the mathematics, it's a little bit more harder. That's why we just did it for a free particle, right? We made these arguments about the space being isotropic, and it's not isotropic anymore once you have a potential energy. And so I'll confess that I haven't looked into how you would do this sort of exact argument for the case of when you have to put a potential energy in it.
Okay, fair enough. It was interesting that we could get the kinetic energy out of it with just some assumptions, so that was cool.
Yeah, that's why I put it in. I thought it was pretty neat. I found that in the Landau and Lifshitz textbook. Okay, any more questions? Okay, well, I'll talk to you guys on Monday, back on the mainland. Bye, everyone.
Holiday.
Well, that's not a holiday, it's a conference.
Yeah, have a good weekend.
Thanks, you too.